Okay, these are some notes for section 7.4, so please make sure you have your textbook open to page 412 and 413, because I'll be referring to this because they have some pretty good write-ups on these. And try to read all this carefully so you understand kind of basically what's going on. But we're going to try to find the arc length. That's what this is all about, finding the length of a curve, what we call a smooth curve. And what we do is just divide the curve into little sections. These are measurable sections. We don't really know how to measure a curve, but we do know a straight line. So we break this up into straight lines, measurable sections that we can use, and then use that Riemann sum process that we've used so successfully previously, and we'll just sum these all up. So if this is the section that I want, and we're going to take more and more of these sections and make them small, make the, as the norm approaches zero, of the partition, then we're going to make these sections smaller and smaller and smaller, so we have little triangles, and then this will conform more to the curve, and then eventually we'll get a exact measurement of the curve length, or the arc length. So we use the Pythagorean theorem process, and we've got delta x, delta y, change in x, change in y, and this is the length that we're going to be using. That's pq, so delta x squared plus delta y squared equals pq squared, so pq equals the square root of delta x squared plus delta y squared. So if we sum all these up, if you look in your textbook, then we'll have the length of the curve. Okay? All right. So if you read in the textbook, it says all we need now is to find the limit of the sum of this sum as the norm of the partition goes to zero. That's the usual plan, but this time there's a problem. Do you see it? The problem is that the sums are not Riemann sums. They do not have that form summation of f of c sub k of delta x, and I'm reading right from the middle, page 412. We can rewrite them as Riemann sums if we multiply and divide each square root by delta x sub k. So that's what we're going to do, and I kind of filled in some of the steps because he did skip some steps over here. So again, kind of take a look at the way the textbook does it, and then after we go through some of these notes, you'll probably be able to follow what they're saying a lot better. But again, if we look at this is what we got by just using the Pythagorean theorem. Okay, so again, if we look at this is what we saw. We had this right here, but this is not a Riemann sum. So we have to get that in the form. Now remember, the Riemann sum form is this form. Okay, remember our summation. And again, our function had to be continuous, so we'll talk about that momentarily. So what we do, or the textbook suggests, we multiply the top and the bottom by delta x sub k. Well, that's just one, so we're not changing the value. Then they move this delta x sub k in the denominator and leave this on the back. So now we have our Riemann form. See some function f of c sub k times delta x sub k. And now we can simplify this to make our calculations a lot easier. So we, again, just square this, and say this is the same thing as the square root of delta x sub k. So now we have both the numerator and the denominator under the radical. Then I can put them under the same radical, and then I can break this up. So I could have this delta x sub k squared over delta x sub k squared, and this delta y sub k over delta x sub k squared. And this, again, is times the delta x sub k. Now this just becomes 1, and this is what we have. Now this is basically the change in y over the change in x. Well, remember, the change in y over the change in x, that's the same thing as f of b minus f of a all over b minus a, right? Change in y over the change in x. That's the same thing. Well, we know by the mean value theorem, as long as our function is CC2, continuous on the closed interval, differentiable on the open interval, we know that there exists some c sub k in this little subinterval, such that f prime of c sub k equals this. So we're going to substitute this for f prime of c sub k. All right. Now, again, we're using the mean value theorem, and this is a real valuable theorem we'll see in some of our theory. We actually saw it in the fundamental theorem of calculus. It was really necessary. So that's why you have to be very, very much aware of everything that's going on with the mean value theorem. So I can make this substitution. Now, we'll talk about why this must be continuous shortly, but well, it must be continuous because this Riemann sum is defined for continuous function. We talked about that when we talked about Riemann sum, so we have to have a continuous function. Remember, the square root is a continuous function on its domain. One's a continuous function, so this must be, x squared is a continuous function, so this must be a continuous function in order for the Riemann sum process to be valid. So this must also be continuous. Okay, so now we can just sum this up. We can change this from over an interval from a to b, and we can just rewrite this as a integral. Over some interval a to b, we'll just change this, and that's going to be f prime of x squared dx. And we've done this before. We've changed the Riemann notation into like the integral notation. And then we just sometimes, instead of saying f prime of x, we write it as dy dx. And there's your basic arc length formula. Okay. So we kind of summed it up over here, so let me see if I can get this in. So these are just a few little things that you want to be aware of. Since we use the mean value theorem, f of x must be CC2. We talked about that. Since we use Riemann sums, we've got this. This is my Riemann sum. This is my function. This must be continuous. And as I just stated earlier, that implies that this must be continuous. Or dy dx must be continuous, the derivative. So not only must the function be continuous and differentiable, the derivative also has to be continuous. Now we talk about this over here. The textbook explains it also. If a function has a continuous first derivative, we say it has the property of smoothness. Smoothness. All right. I forgot an H. Smoothness. All right. Okay, a function with a continuous first derivative is smooth, and its graph is a smooth curve. So we have to have these properties. So my function not only has to be CC2, so the mean value theorem will apply. It also, its first derivative also has to be continuous, so it's a smooth curve. All right. So we've got that. So here we go, and this is what we're going to be seeing on the bottom of page 413, and I just rewrote them, but they're right there. Okay, definition, arc length, the length of a smooth curve. If a smooth curve begins at AC and ends at BD, and A is less than B and C is less than D, okay, then the length, arc length of the curve is given by either one of these formulas depending on which way I'm going, whether I'm using dx or dy. Okay, and it's going to be the same length, it just depends on how you look at it. So the integral from a to b of the square root of 1 plus dy dx squared times dx, if y is a smooth function of x on the closed interval ab, or the integral from c to d of the square root of 1 plus dx dy squared dy. Okay, if x is a smooth function of y on the closed interval cd. So those are our main formulas. And once you get by the theory, they're real easy to apply. And if you know the theory, it's easy to remember them. Okay? And we'll do some examples in a moment. Hope that helps. But again, please remember, read the textbook, and you should now be able to go through the textbook and pretty much understand what they're talking about. And that's just 2 pages, 412 and 413.